think we can start. Yeah.
So budget, we should restart.
Yes.
Okay, so I noticed, I mean, okay, good. I was told, actually, I didn't notice anything. I was told that I just forgot to answer a very good question. Would universality among all invariants? Because I think it's important for people to realize something, which is that isoradial graphs, in some sense, all look like uniform mesh size. If you think about it, they are even built in some sense in the way that they have a uniform mesh size everywhere. So I don't think that isoradial graphs capture, if you want, images by conformal maps where the derivative would not be uniform. Why? I mean, uniform in modulus, sorry. Why? Because, I mean, if you change if you have a conformal map which say has a derivative of modulus 2 in some area and a derivative of modulus 1/2 in another, then if you want the effective mesh size of applying the conformal map to the square lattice, is going to be that in one area, it's going to, I mean, a square lattice of mesh size delta. In one area, you will have a square lattice of mesh size 2 delta, roughly. And in the other one, square lattice of mesh size delta over 2. And this is really not captured by isoradial graphs. So my guess, my guessed answer to this question is that isoradial graphs do not capture this scale invariance at all. That's my feeling. It's not, I mean, a proof of anything, but I would say that rotation invariance is exactly what isoradial graph kind of capture, because there you are really using somehow a map which has a derivative of modulus, which is 1. Okay, but of course it's not a theorem. I mean, maybe there is a way to get more than that. Okay, so let's dive into the proof and start with a fourth point, which is, first, I would like to explain to you how you can transform the square lattice into a lattice L of alpha, and more precisely, I want to explain how you can transform the Bernoulli percolation on the square lattice into a Bernoulli percolation on L of alpha. Okay, and this you should give credit where it's due. This is going to be based on an argument that was introduced by Grimet and Manulescu to study Bernoulli percolation. And the idea is to base the argument on the star triangle transformation. So what is the star triangle transformation? First, at the level of graph. So imagine that you have a graph. Okay, there is a graph, blah, blah, it has connection. And somewhere in this graph, you have a triangle like that. Just a face of, I mean, having 3 edges on its boundary. Okay. Then there is a transformation, a natural transformation that you can do, which is to transform this graph G, let's call it G triangle, into a new graph star. I mean, it's kind of a very lame star with only 3 edges, but I mean, people call it a star, why not? Which is exactly the same lattice, except that instead of having a triangle between 3 vertices A, B, C, you transform it into a star with the same vertices, A, B, C. So you do not modify any, and you just replace the triangle by a star, okay? Well, the star triangle transformation is a way to relate, I'm sorry for all these drawings. I don't know why I didn't erase them. The star triangle transformation is a way to relate Bernoulli percolation on the original lattice to Bernoulli percolation on the new lattice, on the original graph to Bernoulli percolation on the other graph. So imagine you have omega, which belongs to 0, 1 to the G triangular. I want to be attributing it an image configuration, which I'm going to call T of delta of star triangle. So maybe star triangle would be better. But okay, here it's triangle star, but usually we call it the star triangle transformation of omega, which is on 0, 1 to the G star. And I'm going to do it as follows. First thing first, I'm not modifying any edge not on the triangular or star. Okay, so meaning if I have an edge here which is open, well, this edge is also open in the image. Okay, so the only edges I'm going to modify are the edges I must modify, because anyway ABC is not a triangle AB, for instance, is not an edge on the new graph. So I need to modify the edges AB, BC, and CA, but every other edge is put. If it's open in the configuration omega, it's open in the image. If it's closed in the image, okay? Then, that's the first thing. Then the second item is that now I need to explain to you how I modify, how I defined this configuration on the star. And it's going to depend on what was the configuration in the triangle in omega. So imagine, for instance, that the configuration in omega was like that, meaning one open edge and two closed edges. In this case, deterministically, I'm going to decide that the open edges are the two edges, from A to the center and B to the center, and the third edge between C and the center is closed, okay? Notice that this does not modify the connectivity properties of any edge, any vertex. Like if a vertex is connected to another vertex in omega, it's going to be the case in the image by the star triangle, except there is one point which has a different role, which is the center of my star O. Of course, it modifies because it was not existing before, okay? Let me give you another example. Imagine, for instance, that all the edges are open, or that two of them are open. In this case, I would like to modify in such a way that I still preserve these connectivity properties, exactly like in the first transformation. So what is the only possibility to preserve all the connectivity is to actually transform that in such a way that everybody is open. If the three edges of the star are open, I'm certain that whatever the configuration outside, the connectivity properties will be preserved, simply because in this example here, so here I'm guaranteeing the same property, okay? If you think it's a little bit arbitrary what I'm doing, I'm constructing the map. So I'm just telling you that one can construct a map that has the right properties, okay? It remains one case, which is that maybe all the edges of the original triangle are closed. Here again, I would like to be preserving the connectivity. So there are 4 configurations that preserve the connectivity. The first one is everybody is closed, but there is also these 3 configurations that preserves the connectivities. Okay. Well, let me just make you believe, or I mean, you will have to trust me, that one can associate to these properties 3 probabilities, P1, P2, P3, P4, I mean 3 parameters, with P1 plus P2 plus P3 plus P4 equal 1, okay? In such a way, and that's where things are absolutely amazing, in such a way that if I start from omega, which is sampled according to phi L pi over 2, then T delta star of omega is sampled to phi, not phi omega, phi G diamond is sampled according to phi G star. So there exists P1, P2, P3, P4. In fact, the formulas are extremely explicit, but I don't want to be entering into the discussion here. There exists P1, P2, P3, P4 in such a way that if omega is Bernoulli percolation on G delta, G triangle, then T star triangle of omega is Bernoulli percolation, has the law of Bernoulli percolation on G star. Okay? I just realized by doing that, okay, no, let me not. So this is, I mean, it's not difficult, it's just lengthy to prove that there exists P1, P2, P3, P4. So maybe you can believe me and just look in the paper for the formulas for P1, P2, P3, P4. Okay, so there is a transformation like that. So why is it good? To relate Bernoulli, so it relates Bernoulli percolation on G triangle with Bernoulli percolation on G star. But if you apply this properly, it's going to allow us to relate more than that. In particular, imagine that you start with a lattice, and now it maybe answers Trish's question. Start with a lattice where the black lattice is made of lozenges of angle alpha, then squares of angle pi over 2, then one lozenge, what we call track or line, one line of lozenges of angle alpha, again lozenges, I mean square lozenges, and then alpha lozenges. Just for the future, we usually call this a track of angle alpha, and this a track of angle pi over 2. Okay? Okay, so what I want to be convincing you of now is that you can take a graph which is made of tracks and exchange tracks using history. And somewhere at the very end of your track, you imagine that you have.
So sorry, Hugo.
Yeah.
Can you repeat yourself because that was really disrupted?
Okay.
Yeah.
So imagine that very far east, you are at the end of your graph in some sense. Of course, if you are on an infinite graph, there is no end, but you can imagine that maybe you truncate your graph and there is an end very far east. And there, assume that you add a lozenge. Let me remind you that here you have kind of a graph that looks like that. If I draw the looks like that. Okay. So if I go back here, so let's say it does like that, and here like that. Okay, so I'm just trying to draw the graph in some way. So this is the original graph. And imagine that very far on the east side, you add this red, adding the edge like that. So now here, if you think about it, you have a triangle. So what can you do? You can just modify this triangle into a star triangle transformation. And this, if you think about it, it's going to correspond, if I just think of the lozenges, it corresponds to exchanging the position of, I mean, it's moving one step on the left, the red lozenge. Because here, if you think about it, when I move this like that, the new graph here is made of a lozenge, of a star. So the star triangle, maybe that's what I drew here. The star triangle transformation, when you look at isoradial graph, it kind of corresponds to reversing. You see here you have three lozenges. You reverse, you exchange the red lozenge passes on the left if you want, okay? So by moving one step on the left, the red lozenge, you just apply the star triangle, applying the star triangle transformation moves one step on the left, the red lozenge. But then here, now if I ignore all of this drawing, here I'm facing one lozenge and here, if I look at this thing now, I have a star. So what can I do? If I have a star, I can apply the reverse map to get back to a lozenge, which if you think about it, it's going to correspond to moving one step on the left, my red lozenge. I draw now the thing, I end up with a triangle. This is a triangle that I obtain after applying the star triangle. And you keep doing like that. You keep going, pushing step by step the red lozenge from right to left. What you end up at the very end, when the red lozenge is on the left of my configuration, well, you exchange the red track, I mean the track of angle alpha with the track of angle pi. Violet track one step down, okay? Notice that these transformations, they preserve the law of the percolation configuration. So if you start with a percolation omega and you apply this, like these successive star triangle transformations, you end up at the end with a configuration on the new graph where you exchange the two tracks. And if you started with omega with low Bernoulli percolation, you end up with the low Bernoulli percolation, okay? But on the new graph. Okay, notice one thing is that, and this is important for later, omega, even if you start from an omega, you end up with a successive, like let's call it T of omega. So by applying successive star triangle transformations. But notice that the star triangle transformations are not deterministic, right? Because here, apart from all close, 4 possible outcomes. So it's a random outcome, okay? Just keep that in mind. It's going to be important not to think of T of omega as a deterministic image of omega. T of omega is a random variable. It's a random object. Okay. So I explained to you how you exchange two tracks of your graph. Okay, so now from that I can explain the first version of the coupling between omega delta in phi delta L pi over 2 and omega delta prime in phi delta. Okay, so what you do is the following. Start here. Let's look at this picture. Start with a lattice that looks like the square lattice, except that above a certain height, say height n. Just a second. I have a problem. Sorry about that. I had some problem of connection on my side for once. Okay, so imagine you start from a lattice. Sorry about this interruption. From a lattice, which is a square lattice, up to a certain height n, and then you put a rotated version of the square lattice. I mean, sorry, rotate. It completely put me offline. Sorry about that. You put tracks, sorry, of angle alpha. Okay, so you put on one half of the space tracks of angle pi over 2, and on one half of the space tracks of angle alpha. And now imagine that you push down the tracks of angle alpha one by one to try to position them at a certain height minus n below the origin. Okay, so you push one track down until it reaches its bottom position. Then you take a second one and you push it down step by step until it reaches one step above the previous one. And you keep doing like that until picture like that here, where on height 2n, so n below and n above, you only see tracks of angle alpha. Okay, so you started, maybe if I redo a drawing, you started with something that looks like that. And at the end, you want to reach something that looks like that. So you exchange certain tracks to bring them down near the origin. Okay. So here you have n. Okay. The outcome of this is that and before I this, and now I have something that looks like the alpha. And remember that we are looking at Bernoulli. So Bernoulli doesn't care what happens outside of size capital N when you look at events that looks the box. Remember the and distance of equations.
Sorry, Hugo, we lost the last few sentences.
Yeah, I think.
So when you said like the Bernoulli doesn't care, I'm sorry.
Yes, sorry. So when I look only at an event that depends on the box of size capital N, then I don't care about what is outside of the box. For the law of Bernoulli, it's an independent of the edges. Okay. So if I'm only interested in what happened in a certain box nearby the origin, when I do this exchange, I'm starting from something that looks like the square lattice and ending with something that looks like L alpha. Okay. But remember, and this is just to remind you of this, remember that if you start from the if you want to look at the Kamiya-Newman distance and try to prove it's smaller than epsilon, if now you think of this as being mesh size delta, you only look at balls which are, you only look at loops that are within the ball of size 1/epsilon. So only at guys that are close to the origin, okay? So if you take capital N to be something like 1/delta-epsilon, this fact of exchanging n, 2n tracks, or actually 2n/sin-alpha, if you think about it, tracks, is sufficient to change everything nearby the origin from a square lattice to a rectangular. Very good. So from this sequence of transformation, I can define the first coupling. So coupling number 1. So what is it? At step 0, I'm going to define omega 0 to be sampled according to phi L0. So for simplicity, I'm not going to look at the mesh size delta anymore. So I take omega 0 to be sampled according to phi L0, where L0 is really the graph obtained by having tracks of angle alpha above height n and tracks of angle. So this is 0 and this is height capital N. So I want tracks of angle alpha and tracks of angle pi/2 below. Okay, that's L0. So I sample omega 0 according to phi. To do is the following. I'm going to take omega t+1 to simply change by a track exchange. This is a track exchange of omega t. It's going to be maybe is change exchanging alpha with the track of angle pi/2 that you get by basically starting with L0, bringing one track down. So first step, for instance, is going to be exchanging this track. Then, as we said, we are going to be like that with a track like that. Now, with this one, you go back, you go like that until you reach, you put the track of angle alpha at distance, n tracks below the axis 0. Once you have put this, you decide that this is final position. By the way, it happens at time 2n, because you had to exchange the track of angle alpha with 2n tracks of angle pi/2. And then you go back at the top, you pick your first track at the top, and you bring it down until it ends just here. This is going to be happening at time 4n. Then you keep the track you take the track at the very top, you bring it down until it happens, it arrives here, etc., etc. You do that, if you think of it, each 2n times you brought one track from the top to the bottom, and you need to do it in such a way that you, at the very end, end up with something of Euclidean height 2n. So you need to bring 2n/sin-alpha tracks of angle alpha. So you are going to do that for this time. So the process, they are going to be capital T equal 2n times upper part of 2n over sine alpha steps. And after this capital T steps, you exchange sufficiently many tracks that it looks like a lattice of angle sine alpha. Okay, so this is every single time doing the right track exchange. I don't want to be telling you exactly what this is. I mean, there is a formula, but it's not really relevant. I think we can at least get a vibe of what is happening by just saying you are doing the right track exchange. Okay, so this is the first coupling. Notice that this first coupling has a certain number of properties. First property is that if omega 0 is indeed sampled as phi L0, then omega t is sampled according to phi LT, where LT is the image under the track exchange of L0. Okay, so it's just the graph you obtain at the very end. So if you started with omega 0 with the right law, you end up with omega t with the right law. That's the first. The second thing is that the clusters, so the connected components of omega t, are only modified locally. And this is really something important. What do I mean by that? Remember that I told you that the star triangle transformation is only modifying, it's not modifying any edge outside of the star or the triangle that you are modifying. And the connectivity properties here are not modifying the connectivity. I mean, the transformation is such that it doesn't modify the connectivity properties except maybe at the center of the star. So when you do successive applications here, you are only modifying locally the clusters. Okay. Third property is that the cluster, I mean, so okay, so what you would like to be proving, and this is, I mean, I realize that I'm on the wrong computer to show you the simulation, which is yet another consequence of the poor internet. If you look at simulation of the star triangle transformations, you realize that when you look at big loops in your configurations, right? You look at the boundaries. These big loops, they are not really modified by the successive star triangle transformations, the successive track exchanges. So it seems that large clusters, but this is something less clear, large clusters do not move too much under the transformation. So this is very good news because in some sense, that's exactly what we want to prove. The problem is that it's not straightforward. So these 2 points, 1 and 2, were consequences of the definition. On the other hand, the third item is something you need to prove. You can see it on simulations, but you need to prove that large clusters do not move. And that's basically where all the juice of the paper is. So here, what we kind of need to prove is that large clusters, I mean, we need to prove this property. And this is really all the work in some sense. Let me just mention because we are here discussing observations, let me mention two simple observations regarding the transformation. The star triangle transformation is also preserving, it preserves inclusion between large loops. Why? Imagine you have a loop that is surrounding another loop. Then the only way, so there's a loop gamma and a loop gamma prime. We know from property 2 that gamma and gamma prime are modified only locally through the star triangle transformations. And it's possible to prove that the only way it could, gamma could cease to be surrounded by gamma prime is if gamma disappears. That's the only possibility. Otherwise, gamma is going to be modified locally, but it cannot somehow start moving outside of the large loop, okay? Or gamma prime cannot enter into gamma. So there is preservation of the inclusion. This is a very cool property, but there is an even cooler property, is that if you have inclusion preservation, then you also have preservation of the following property, or almost. You want to be saying that the homotopy class of the loops, when you look at them with respect to a punctured plane, where you remove, say, every epsilon, remember we rescale the lattice, right? Every epsilon you remove, you remove a point, okay? And you look at the homotopy classes of the loops in R2 minus these points. Well, you are very much tempted to say that the transformation, the star triangle transformation, also preserves these homotopy classes. Why? Because here, if I modify a little bit through here, it seems like it's not going to change the homotopy class with respect to these points. The problem is that this is not quite true, because you see, maybe the loop was coming very close to a point, and through the star triangle transformation, pass on the other side of this point, and then change completely homotopy class. But if you think about it, since you have inclusion between loops that is preserved, what you can do is not look at the homotopy classes around points of the plane, but rather around kind of small clusters, but not too small, like intermediate size clusters, that are nearby these points of the plane. Okay, so this, imagine that I give you, and I realize that I'm starting to be a little bit vague, but imagine I'm telling you that there are like small clusters that we like to call nails, that there are nails nearby points of the, I think you lost me right now, so I'm going to restart the last two explanations. So imagine that you have nails nearby each vertex of this kind of, around all these points. So you have small clusters or small loops that are nearby these points. Then the loops, the red loops, the homotopy classes of these loops around the R2 minus the nails these times, this is preserved by the transformation. So this fifth point could be summarized as follows. The homotopy classes around nails, so nails being these small clusters nearby the points, are preserved. So let me finish a little bit. Let me finish this class with a second version of the coupling. So I had the first version. Let me conclude with the second version. And this second version is going to be a lighter version than this coupling number one. Because the problem of this coupling is that it lacks many properties that we would like to have, in particular ergodic properties. This property, maybe it has them, but we have no clue how to prove it. So this second coupling is going to be a way to contour the difficulty. And it's going to be based on the following idea, is that instead of keeping track only, of keeping track of the whole configuration, we are going to keep track only of these nails that I didn't properly define, but imagine clusters nearby the points of our lattice. Is that correct that the nails can slightly move under the first coupling? It's a very good question, Misha, and I'm going to answer it in a second. It's actually the whole heart of the proof, and this is a very good question. So nails are going to be keeping track of, and homotopy classes of loops are going to be keep track of. So here, let me call H of omega to be the following information. It's going to be the set of nails, so the set of large clusters. I don't of these clusters nearby the points. Really, all the information on the nails. So what I'm going to keep track of is just of the smallest rectangle that is containing it. So if you have a nail, there is a smallest rectangle that is containing it. I keep track of all these things. And second thing, I keep track of what I call the homotopy classes of loops around nails. Of course, many loops will have trivial homotopy class, but some of them will have non-trivial homotopy classes. And if here epsilon is sufficiently small, these homotopy classes will tell me a lot about the geometry of the loops. And the coupling number two is going to be the same as before. So for step 0, you take omega 0 sample according to phi L0. And from step t to t plus 1, well, I'm going to do the following. First, I'm going to do an intermediary step where I'm going to sample omega t plus 1/2 according to phi LT. So LT is just a graph you obtain by doing t transformations, okay? And I'm going to just resample according to the fact that h of omega t plus 1/2 is equal to h of omega t. So what do? Basically, I take omega t and I just resample a new independent configuration, just conditioned on having the same set of nails and the same homotopy classes for the loops. This resampling is going to give me a lot of independence in my new step, but still keeping track of the relevant information if you want. And then from step t plus 1/2 to step t plus 1, I'm going to simply define omega t plus 1 to be the image by the t transformation of omega t plus 1/2. I think this is a very cool kind of trick to keep in mind when you are studying a Markov chain and your Markov chain is lacking some renewal properties, some independence properties. What you should think of is think of the information you want to keep in mind from this Markov chain and just resample at every step according to just the law that you obtain when you condition on this information. Okay. from that, there is somebody who remove, yeah, perfect. From that, what remains to be done? There are two things that needs to be done, and I'm not going to do them now, but I just want to mention them. So first thing, I told you that the homotopy classes around nails, I mean that the nails and the homotopy classes around them is relevant, I mean, is the only relevant information I need to keep in mind. Well, it's not that obvious. So first thing you need to prove is that information on nails and homotopy classes enable to prove, I mean, to measure the distance between two configurations. This is a very cute theorem in our article, which is basically saying that if you know the homotopy class of a large loop, basically you know its geometry. And this is due to the fact that loops at criticality are typically fractal and that they are going to have very wide homotopy classes with respect to points in the, I mean, regularly spaced points in the plane, or with respect to nails for what matters. So you can reconstruct the geometry out of the homotopy classes. So it's indeed sufficient to keep track of homotopy classes. But it's only sufficient if you are able, and this goes back to Misha's question, it's only sufficient if, I mean, it's sufficient only if you can prove that the nails do not move. You see, imagine I tell you the homotopy classes with respect to regularly spaced points. If I tell you that two large loops have the same homotopy classes, then, well, you see, maybe they can be a little bit different, but typically they are going to be close to each other. Now imagine that these points are not at the same position for the red and the green loop. Then the homotopy classes will give you zero information on the geometry of your loops if you don't know where the points are. So a big piece of the, I mean, the whole, in fact, heart of the proof will be to prove that the nails themselves do not move. So here we need to prove and in order to do that, there is really a lot of things that needs to be proved. And one important item is that we need to invoke informations from exact integrability, basically. So I don't want to be entering in opening the door in some sense that behind here I'm only talking about probabilities, but behind these probabilities and this probabilistic study, there is a whole world of integrable probabilities that we need to invoke, and which was done in another paper of us with, I mean, with the same author plus Tatiana, which is another person. And yes, I think I have missed something. You mean the nails or the smallest rectangle? The smallest rectangle containing the nails. Yes, Trish. So the smallest rectangle containing the nails should not move too much. But you see, I mean, if they don't move, then the nails themselves do not move, right? Because in some sense, the rectangles are kind of an envelope of the nails. So if the rectangles do not move, the nails do not move either. Okay, I think I'm going to stop here because I feel like everybody is tired. At least I'm tired. I don't want to be entering. I won't have time in 5 minutes to tell you anything relevant on this exact integrability side. So I think I prefer to stop here and leave you with this idea that there is this second side of the coin in some sense, which is necessary to prove the result, and which is coming from very different ingredients. Okay, thank you very much for your attention, and I'm looking forward to answer your questions. Thank you.
Okay, thanks, Hugo. Let's thank Hugo for this wonderful talk.
And I'm really sorry for the poor internet. It kind of threw me off balance. Okay,
so,
are there questions?
Yeah, so I think are there questions that you would like to ask Hugo?
I mean, some people already asked questions, so maybe there are no questions anymore. But...
Can you explain why n is 1 over delta epsilon? I didn't understand.
Yes, so you want to be, I mean, I drew things like it was on the square lattice of mesh size 1, roughly, right? But in fact, I'm looking at mesh size delta, and what I want is I want a ball. I want to be controlling everything in the ball of size 1 over epsilon, right?
Okay. Yeah, okay, I see it.
Sorry, what is that?
So there's a question in the chat box. Is life any easier if it considers a perturbed lattice or the Poisson-Boolean model?
Is life easier if one considers a perturbed lattice? No. It becomes much harder because we need to control actually this integrability properties is, I mean, they are very dependent on the lattice, in fact, much more than, so you want a very regular lattice. So it's much worse on Poisson-Boolean or on perturbed lattice, yeah. Okay, if there is no other questions.
Yes,
then...
so if, then, okay, let us thank Hugo again for this wonderful series of 2 talks.
Thank you very much for your attention, and
it was a great pleasure for us. Yeah. Okay.
Hoping to see you around one
guys.
day.
See you
Bye-bye.
around.